All right, here we go. This is proposition 26, the angle side angle criterion. We're going to go ahead and try to prove it. So first things first, we have to have some triangles. All right, so let's just let triangle ABC, we have triangle ABC, and triangle, we'll say triangle DEF. Okay, let these exist such that, so we have some angle side angle criteria. So let's go ahead and say that angle ABC is congruent to angle DEF. Let's go ahead and say segment BC is congruent to segment EF. And we need another angle. So we'll say angle BCA is congruent to angle, say, EFD. EFD. Okay, so now from here, what I'm going to do is I'm going to mark this on my picture. I tell my students all the time, whenever you know something's congruent, mark it on your picture. And you know what they do? They don't do it. All right, so there we go. So we have an angle side angle criteria right now. So if we just look at this right now, so let's just say, so if that was supposed to be a star, so if AB is congruent to DE, right, if AB is congruent to DE, well, then notice we'll have an SAS criteria. So AB is congruent to DE, angle B is congruent to angle E, and BC is congruent to angle E. Then we're done. So if that holds true, by proposition 4 is SAS, by SAS, triangle ABC is congruent to triangle DEF. Okay, so that's a little bit too easy. That feels like cheating. So let's go ahead and assume that they're not equal. All right, so here's what I'm going to do. I'm going to go ahead and erase all of this, and we're going to put a slash through our congruent sign. All right, so now let's go ahead and assume that they are not congruent. So we can say without loss of generality, let's just let AB be greater than DE. And what this means that without loss of generality, what that means is I could say AB is less than DE, and we're going to have a similar proof, except we're going to use DE instead of AB. All right, now from here, since AB is greater than DE, if we look at our axiom list, C1, the first congruence axiom, says that there exists a point. There exists a point on array such that we can have one segment being congruent to another. So since AB is greater than DE, what we can do is we're going to go ahead and put point ABCDEF G. We're going to put point G on AB, and we're allowed to do that. We can put a point wherever I want. So what we're going to have is let point G be on AB. All right, and it's going to be on AB such that it's between A and B. So we're going to say A star G star B. All right, so what that means is G has to be between A and B. And since we can put G anywhere we want, it's going to be helpful to construct G in a spot where BG is going to be congruent to DE. That's what we have is something like this. And now what I can do is I am going to make a segment GC. Now, if we look at GC, or if we look at triangle GBC, right, let's just write this down. So notice that triangle GCB triangle GCB is going to be congruent. GCB is going to be congruent to DFE. Triangle DFE. All right, now, why is that? Well, we know this is congruent by the side angle side theorem, by SAS. All right, so GB is congruent to DE, that's one of our sides. Angle B is congruent to angle E, that is our included angle. And then BC is congruent to EF. We haven't changed that one. So by SAS, we know that these two triangles have to be congruent. And this is useful because in my high school class, we call this the CP-CTC theorem, where the corresponding parts of congruent triangles must be congruent. And what that means is if we have two triangles that are congruent, then all the other parts have to be congruent as well. So what that means is, my little apply symbol here, is we know that angle GCB must be equal to angle DFE. All right, just make sure it all lines up. So triangle GCB is congruent to DFE, so therefore the angles are also congruent. Right. Now, this is useful because if we look back up at our assumptions, we know that BCA is congruent to EFD. Okay, and one thing I did write them backwards, so angle EFD is the same thing as angle DEFD and DFE are congruent. It doesn't matter which way you write them, as long as that middle letter, that's the important one. All right, so what we can do is we can use our transitive property to tie these together. So I do a darker color here. I know that angle GCB must be congruent to ACB. ACB, or here, I'll just for consistency, we'll call this BCA. BCA. All right, so we know GCB is congruent to angle BCA, and this is the transitive property. Okay, now from here, this is good. It's bad, but it's good. All right, so what I'm going to do is I'm going to try to draw out a contradiction. Since these two angles are congruent, what we must have is, let's kind of look, I'm going to do a side note. And so if we look at these two angles, so I have B vertex C. I know that these two angles are congruent. So what I'm saying is, here was our original point A. All right, and since these two are congruent, they share side BC. So since they share side BC, what we must have is we must have that G is also somewhere on AC. So we either have two situations. Maybe G is between A and C. Maybe A is between G and C. All right, so let's go ahead and write that down. So either, different color here. So we must have either G A C or AGC. Right? And normally that's not a big deal. But if we look up at our assumption, or not our assumption, but the way that we constructed point G originally, right? We originally let G be a point on AB. So what this means is that point G is lying on two lines, which is okay in some instances, but these two lines have more than one point in common. So essentially, GA is on both line BA and GA is both on line AC. And that is a contradiction. Let's go ahead and just draw a picture of that. So we had, let's go back up here for a second, BGA So this is B, G, A. This is by construction. And what we just showed is that we have point C right here. And there is another line that does something like this. And we know by our axioms, by our incidence axioms, right? For any two distinct points, there is a unique line going between them. All right, so this right here violates I1. It violates our very first axiom. So this is a contradiction. So the only way to get around this, so we must have that points G is the exact same point as point A. They are indistinguishable. So G and A have to be the same point. All right. So since we showed that the two triangles were congruent, so since triangle GCB is congruent to triangle DFE, what we just showed is that G and A are the same thing. We must have triangle ACB must be congruent to triangle DFE. Right. And there we have it. So what we did is we showed that the two triangles, the new triangle, were congruent by the side angle side theorem, but the given information used angle side angle. So what we did is we showed that the angle side angle criteria holds, and that is a legitimate way to show that two triangles are congruent. Now, the next part of proposition 26 is the angle side proof, and that is it's a similar argument you give. You do a proof by contradiction. You use the side angle side theorem. Very similar to this one. So in the interest of time, this video is getting a little bit long. I think I will go ahead and omit that one.